Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss network theorems. In the previous class, we have discussed about superposition theorem and as well as Millman's theorem. The superposition theorem and the compensation theorem. And in today's class, we are going to discuss about some more theorems, which are Thevenin's, Norton's, and the maximum power transfer theorem. Right. So first, let us go with Thevenin's theorem. So first, let us see the statement of the Thevenin's theorem. Actually, what it states here, the Thevenin's theorem states that again here, of course, as we discussed in the previous class, all the theorems. These theorems should apply for linear and bilateral networks, right? So here also, this Thevenin's theorem states that any linear bilateral network containing several voltages, currents, and resistances can be replaced by just one single voltage source in series with a single resistance connected across the load. So, which means here, if you want to find a response across any element, either it may be voltage or the current flowing through the resistance, then the total circuit can be replaced by an equivalent circuit. That equivalent circuit consisting of one single voltage source, which is called as a Thevenin's voltage source, or also called as the open circuit voltage source, and in series with a single resistor, which is called as a Thevenin's resistor, connected across the load terminals. So load means through what resistor we need to find the current. That is, we usually consider as a load. Okay. Then how we can find these? What is this Thevenin's voltage and what is this Thevenin's resistance means? Here the Thevenin's voltage is the open circuit voltage measured in between the load terminals, and the Thevenin's resistance is the equivalent resistance measured across the load terminals when all the voltage sources are replaced by the voltage sources are replaced by the short circuit and the current sources are replaced by the open circuit. So this is the Thevenin's theorem. Let us discuss in detail about this Thevenin's theorem. So let us consider this is a linear or bilateral network. So let us consider here RL is the load, which means here we need to find the current flowing through this resistor. So that's why here we are just considering as a load resistance RL. So this total circuit is replaced with a Thevenin's equivalent circuit. This circuit is also called as a Thevenin's equivalent circuit. So the Thevenin's equivalent circuit consisting of a single voltage source V Thevenin's and in series with a single resistance, which is R Thevenin's, across the load. Here this is the load. So across the load, this is the load R. Right? So then what is V Thevenin's or VOC? This is the open circuit voltage measured between the load terminals. And what is R Thevenin's? Is the Thevenin's equivalent resistance across the load terminal when all the voltage sources are replaced by the short circuit and all the current sources are replaced by the open circuit. Then from here, actually what we need to find current I. So from here we can say from this circuit I is equal to V Thevenin's by R Thevenin's plus RL. So in this way we can find the current flowing through the load resistance RL. Okay. So for that, let us consider one example. Okay, a simple circuit. For this circuit, we need to find the current flowing through 3 ohms resistor, which is this one. Okay, so which means here, this is RL. We can consider it as a RL. So which means where we need to find the the current, which is the current flowing through the 3 ohms resistor using the Thevenin's theorem. So now what we have to do according to the Thevenin's theorem, first we should replace these total circuit into one equivalent circuit. Okay, that equivalent circuit consisting of one V Thevenin's, okay, and in series with R Thevenin's connected across the load terminals, right? So which means this is V Thevenins and this is R Thevenins and this is RL, which is equal to 3 ohms. So we need to find V Thevenins and R Thevenins. Okay, then substitute here. Then from this circuit, I is equal to V Thevenins by R Thevenins plus RL. So that we can find I. Right? Fine. So let us see how we can, how to find V Thevenins and R Thevenins. And after finding V Thevenins and R Thevenins, okay, so how we can find the current flowing through the load resistor by using this Thevenin's theorem. Right? Yes, here you can see we should replace with this equivalent circuit, and in this equivalent circuit we should find V Thevenins and R Thevenins. First, let us find R Thevenins. Okay, so according to the statement, where we need to find the R Thevenins? Across the load terminals. So what are the load terminals? These two are the load terminals. So we should find the resistance, the equivalent resistance, which is R Thevenins across these two load terminals. Okay, when the voltage sources are replaced by the short circuit and current sources are replaced by the open circuit. But anyway, here we don't have any current sources. Okay, only one voltage source is there, and this voltage source must be replaced with short circuit. Let us see. Okay, so here you can see in this circuit, we are finding the R Thevenins across the load terminals. Okay, and we are replaced the voltage source with the short circuit. Now find the equivalent resistance between these two terminals. Okay, so here as you can see, 4 and 5 ohms are in parallel. Then 4 into 5 by 4 plus 5. So we can replace the equivalent resistance, okay, by these two combinations. So here you can see. Okay, so that equivalent resistance value is 2.2 ohms, 2.22 ohms. So here, now these 2.2 ohms and these 2 ohms are in series, right? Then 2.22 plus 2 ohms, which is equal to 4.22 ohms. So here R Thevenins, which is equal to 4.22 ohms. R Thevenins is equal to 4.22 ohms. So this is the way to find the R Thevenins. How to find the R Thevenins? First, we should know where we need to find the R Thevenins. Okay, so which is across the load terminals. Here, load terminals means the load resistance means where we need to find the current. Okay, so that we can consider as a load resistance. Okay, then across the load resistance, and again we need to replace the voltage sources as a short circuit and the current sources as an open circuit. But in our given network, we are having only voltage source. So that's why the voltage source is replaced by the short circuit. Yes, now we got R Thevenins. The next step is we need to find V Thevenins. So what is V Thevenins according to the statement? V Thevenins is the open circuit voltage across the load terminals. So which means again, the open circuit voltage across these two load terminals, right? So write the open circuit voltage across these two terminals. Okay. So now we need to find the voltage across these two terminals. Okay. So how we can find the voltage across these two terminals? Okay. Of course, we are having only one loop. Okay, just we can apply the simple Ohm's law, then you can find the voltage across these two terminals. The voltage across these two terminals is nothing but the voltage across the 5 ohms resistor. Okay, because these 2 ohms is connected to this open circuit, so that's why the current flowing through this I is equal to 0. So which means V is equal to also 0. So that's why the voltage across these two terminals is nothing but the voltage across the 5 ohms resistor. Okay, so now I is equal to the current flowing through, because as you know, V is equal to I into R. So if you know what is the current flowing through these 5 ohms resistor, then we can find the voltage across these 5 ohms resistor. Okay, so to find the current flowing through 5 ohms resistor, just simply apply the Ohm's law. Okay, I is equal to V by R. So we know what is V, which is 20 volts, and what is R, 4 plus 5, because 4 and 5 are in series, right? So 4 plus 5, which is equal to 2.22 amperes. This is I. Then V Thevenins is equal to, okay, according to V is equal to I into R, so 2.2 into 5 ohms. Okay, so that we can find the V Thevenins, which is equal to 11.11 volts. So now we got the value of V Thevenins and as well as the R Thevenins. Then substitute these two values in this equivalent circuit, V Thevenins and R Thevenins. Okay, so from that you can find the current flowing through this circuit or this load resistance I is equal to. So I is equal to, again same Ohm's law that here we are applying. V is equal to, here the V Thevenins is V Thevenins is 11.11 by R Thevenins plus RL. R Thevenins is here 4.22 plus RL is equal to 3, which is equal to 1.538 amperes. So this is the way to find the current flowing through the load resistance by using the Thevenin's theorem. Very simple. Okay. So let me just conclude this Thevenin's theorem. Okay. So according to the Thevenin's theorem, the given circuit is replaced with the equivalent Thevenin's circuit, and the Thevenin's equivalent circuit consisting of Thevenin's voltage source in series with the Thevenin's current across the load resistor. So which means here the Thevenin's voltage source and the Thevenin's resistor and the load resistance, both three are connected in series within the circuit. Okay. Then find V Thevenin's and R Thevenin's and substitute in this circuit, so that you can find the current flowing through the load resistance. Then how to find the R Thevenin's? Okay, first where to find the R Thevenin's. So R Thevenin's is nothing but the open circuit, the equivalent resistance across the load terminals when, at what condition? When all the voltage sources in the given circuit are replaced with the short circuit, and all the current sources present in the circuit are replaced with the open circuit. Right? And when coming to the V Thevenin's, here V Thevenin's are also called as a VOC, V open circuit voltage. So the open circuit voltage is nothing but the voltage across the load terminals. Okay, the voltage across the load terminals. So we should open the load terminals. Okay, across those load terminals, we should find the the voltage. That voltage is called as a Thevenin's voltage. Then finally, I is equal to what is that? V Thevenin's by R Thevenin's plus RL. Then you can substitute here the values so that we will get the current flowing through the load resistance. Right? Then next we will go for the next theorem, which is Norton's theorem. So which is something similar to the Thevenin's theorem. If we understood the procedure for the Thevenin's theorem, then it is very easy to understand the procedure for the Norton's theorem. Okay, so here only the difference is, here also we will replace the given circuit with the equivalent circuit. Okay, but here that circuit is called as a Norton's equivalent circuit. Okay, and in the Norton's equivalent circuit, okay, so same like in the Thevenin's circuit, what are the the elements are there? V Thevenin's, R Thevenin's and RL. But here instead of V Thevenin's, here we are having IN, which is Norton's current. Okay, so which is Norton's current, and also a Norton's resistance. But here the Norton's current and Norton resistance are connected in parallel with the load resistance. That is the only difference between the Thevenin's and the Norton's theorem. That's why here is the statement, as you can see, the Norton's theorem states that any linear bilateral network containing several voltage and current sources, okay, and resistances can be replaced by single current source, which is called as a IN or Norton's current source, or we can also call it as a short circuit current. Okay, I will let you know why we are calling it as a short circuit current. Okay, and in parallel with single resistance, which is called as a Norton's resistance, okay, or open circuit resistance, connected across the load. Okay, there, okay, and where IN and ISC is the short circuit current measured between the load terminals. Yes, because before it was V Thevenin's and VOC. Okay, so because the open circuit voltage, but here it is short circuit current. So that's why the Norton's current is also called as a short circuit current. Okay, across the load terminals. And RN is the Norton's equivalent resistance across the load when the voltage sources are replaced with the short circuit and current sources are replaced with the open circuit. So which means the procedure to find R Thevenin's and R Norton's is same. Okay, right. So now let us see how the Norton's equivalent circuit will looks like here, because here, as according to the statement, is replaced with just one single source in parallel with the Norton's resistance. So here this Norton's current source is in parallel with the Norton's the Norton's resistance, okay, across the load terminals RL. So here these three are connected in parallel, but in the Thevenin's theorem, those three are connected in series. That is the only difference between the Norton's and Thevenin's theorem. Okay, so let us take the same circuit. Okay, to find again the current flowing through the 3 ohms resistor by using the Norton's theorem. Of course, anyway we will get the same value, but let us see the procedure, how to follow the Norton's theorem procedure to find the current flowing through the 3 ohms resistor. Okay, so first what we have to do, we have to just draw the equivalent circuit for the given circuit, which is the Norton's equivalent circuit. So the Norton's equivalent circuit consisting of Norton's current source and as well as the Norton's resistance and as well as the load resistance. These three are connected in parallel, right? So in this, first what we have to find, let us find the Norton's resistance first. Okay, then after that we will go for the Norton's current. First let us find the Norton's resistance. So as I told you, okay, the procedure to find the Norton's resistance is same like the procedure to find the Thevenin's resistance, right? So here in the Norton's resistance also, where we need to find across the load terminals, okay, which are here. And how to find? Okay, so when all the voltage sources are replaced by the short circuit and all the current sources are replaced by the open circuit, right? Of course, anyway, in this in the given circuit we are having only voltage sources. That's why the voltage source is replaced with the short circuit. Then now find the R Thevenins. Of course, here also you will get the same value R Thevenins. Okay, whatever the R Thevenins value that we got in the previous case, the same value you will get here. That which is also called as a R Norton's, right? So because again these 4 ohms and 4 ohms and 5 ohms are in parallel. So 4 into 5 by 4 plus 5. Okay. Then the equivalent resistance is 2.2 ohms. And again here these two are in series. So here 2.2 plus 2, which is equal to 4.22 ohms. So here the Rn is equal to 4.22 ohms. In the previous case also, when we are discussing about the Thevenin's resistance is also same 4.22, because the procedure to find the R Thevenin's and the procedure to find the R Norton's is same, right? That's why we got the same value, because we applied these two theorems for the same circuit, right? Okay, now we got the value of the R Norton's. Now we are going to find the value of the I Norton's current. Okay, so here the procedure to find the Norton's current is, before it was open circuit voltage, and this Norton's current is also called as the short circuit current, which means here we are going to make these load resistance are replaced the load resistance with the short circuit. Okay, then find the current flowing through the short circuit, which means whatever the current flowing through this 2 ohms resistor is same as the current flowing through this short circuit, because these two are connected in series, right? So how to find? Okay, either you can apply the current division rule or you can apply a simply loop analysis to find the current flowing through the 2 ohms resistor. Okay, so suppose let us consider loop analysis. This means let us consider this is I1 and this is, let us consider IN or ISN. Okay, then apply the loop analysis, then you can find ISN by solving these two equations, right? Okay, so this is loop 1, let us consider I1, and loop 2, let us consider IN. Okay, write the loop equation for the loop 1 and write the equation for the loop 2. Then solve these two equations. By solving these two equations, we will get I1 and IN. So here IN is nothing but the short circuit current. Let us write here IN is equal to, so now we got Rn and IN for this particular circuit, and we know what is the RL value, which is RL is equal to 3 ohms resistor. Okay, now find the value of the what is that the current flowing through this resistor, this RL. Okay, how to find? A simple way, because here you just apply, of course here this is Rn. Okay, so now you know the total current I. Okay, now let us consider this is I1 and I2, then apply the current division rule. So here I2 is equal to the total current I into, okay, the opposite resistor, which is Rn by Rn plus RL. Then substitute the values all, because we know what is the value of I, we know what is the value of Rn, and we know what is the value of RL. Then substitute, you will get I2 value, which is the current flowing through the load resistance. Okay, so which is the current flowing through the load resistance, which is 1.538. Of course, by using the Thevenin's theorem also we got the same value, because here we considered the same circuit. Okay, and our aim is to find the current flowing through the 3 ohms resistor. Of course, we followed the different theorems, but our target is same, to find the current flowing through the 3 ohms resistor. So whatever the procedure that we are following, we will get the same value, because the network is same. Okay, And our target is also same, that we need to find the current flowing through the 3 ohms resistor. So this is the procedure to apply the Norton's theorem. Okay, so almost, of course, 50% of the procedure is same like the Thevenin's theorem, because here also we need to find Rn, that is R Norton's, is same like the R Thevenin's. Okay, right? And here, of course, there the 3 elements, containing the Thevenin's equivalent resistance, which is V Thevenin's, R Thevenin's, and RL are series. But here, what is that? I Norton's, okay, and R Norton's, which means Norton's current and Norton's resistance and the load resistance are connected in parallel. That is the only difference between the Thevenin's and Norton's. Okay, so I hope everybody is clear about this Thevenin's and Norton's theorem. The procedure, how to find the flow, the current flowing through the load resistance by using Thevenin's theorem as well as the Norton's theorem. Next, we will go for the third theorem, which is the maximum power transfer theorem. So, in the maximum power transfer theorem also, okay, the procedure is almost same like the Thevenin's theorem. So, that's why the Thevenin's theorem procedure is very, very important. So, everybody should know how to find V Thevenin's and how to find R Thevenin's. Right? So, here let me see, according to the maximum power transfer theorem, which means here, just we are getting the condition, okay, at what condition the maximum power will flow through the load resistance. That is states this maximum power transfer theorem. Okay, so here let me read the statement. The maximum power transfer theorem states that in any linear bilateral network, maximum power is delivered to the load. Okay, when the maximum power is delivered to the load, when the load resistance is equal to the internal resistance of a source. Okay, so which means if it is a voltage source, then the internal resistance is in series with the voltage source, and if it is a current source, then the internal resistance is in parallel with the current source. Okay, so that's why here let us consider here the Thevenin's equivalent circuit. In the Thevenin's equivalent circuit, when the maximum power will flow through these RL, when RL is equal to the internal resistance of the voltage source. Here the voltage source is Vs and the internal resistance is Rs. So when RL is equal to Rs, and here also when RL is equal to Rs, the maximum power will flow through this resistance. Okay, so here as you can see, then how to find that maximum power which is flowing through the resistance. Okay, so we know here for this particular circuit, I is equal to Vs by Rs plus RL. Then as we know, P is equal to I square into R. So we know I value, I is equal to Vs by Rs plus RL. Then substitute here. Okay, then P is equal to V square into R by Rs plus RL. Okay, so if you want to find the condition to get the maximum power, then we have to derive this power with respect to load resistance, because here the load resistance is the only variable. Okay, load resistance and equal to 0, then you will get the condition to get maximum power. Just apply the derivation for this. Okay, because you know how to apply the derivation for this, because here the RL, the variable is present in the numerator as well as the denominator. So that's why you should apply this formula to apply the the derivation to this particular equation. Then after applying the derivation, then equal to 0, then you will get RL is equal to Rs. So this is the condition to get the maximum power which is flowing through the load resistance. Right. So let us take some example to check whether when RL is equal to Rs, whether the maximum power is flowing through the particular load resistance or not. So further, let us consider a simple circuit, and in the simple circuit, let us consider the values for the Vs and Rs. And according to our condition, when the maximum power will flow, when Rs is equal to RL, right? So let us consider different values for the RL. Let us consider RL is equal to 1 ohm, then the power is 2.778 watts, and let us consider RL is equal to 3 ohms, then the power is 4.68, and when Rs is equal to 5, RL is equal to 5, then the power is 5 watts. Okay, which means here Rs is 5 and RL is also 5. Then if you consider RL is equal to 7, okay, then the power is again decreasing. If RL is equal to 9, again the power is decreasing. Okay, so which means, of course, for the different values of RL, other than 5, okay, if you consider the values below 5 and are above 5, in both the cases the power is less than the 5 watts. So which means when RL is equal to RS, the maximum power will flow. Okay, if you draw the waveform, okay, in between P and RL, see, you can see here, at this particular, when RL is equal to RS, you are getting 5 watts. Okay, but before this value is, the power is less than this particular value, and after, the value, okay, when RL is increasing also, okay, the power is getting decreased. Right, so that's why here the maximum power transfer theorem states. So let us consider one example. Right, so for this particular circuit, find the value of RL, okay, the load resistance for the given network below that the power is maximum. Okay, so which means here what we are going to find, we are going to find the R Thevenin's value, and whatever the R Thevenin's value which we are getting, the R Thevenin's is nothing but the RL, because here they are giving the condition that the maximum power is flowing. And also find the maximum power through the load resistance by using the maximum power transfer theorem. Right, so first here again for that, okay, so we are just applying the Thevenin's theorem to find V Thevenin's and R Thevenin's. Right, so the same way here. Right, so first we are going to find R Thevenin's. So already we discussed how to find the R Thevenin's. The R Thevenin, first where to find the R Thevenin's? Across the load terminals, which means here. Okay, and when all the voltage sources are replaced by the short circuit and current sources are replaced by the open circuit. Right, so here you can see here just we are making the open circuit across the load terminals, and here these 6 volts is replaced with the short circuit. Now find the equivalent resistance across these two terminals. Okay, so just apply the series and parallel combinations. As you can see, 6 ohms and 6 ohms are in these 6 and these 6 are in parallel. Okay, so and find the equivalent resistance and replace these two combination with the equivalent resistance. Okay, so here I am just replacing, right, and then now these 3 ohms and 2 ohms are in series. Okay, then replace 3 plus 2 5, and again these 5 ohms or 5 ohms are in parallel. Okay, then the equivalent is 2.5 ohms. So which means here the RL, which is equal to 2.5 ohms, because this is R Thevenin's is equal to RL. So when the maximum power will flow, when R Thevenin's is equal to RL, so that's why here R Thevenin's is 2.5 ohms, so that's which is RL, so which is equal to 2.5 ohms. Now find what is that maximum power flowing through this load resistance. So further we need to find the VOC or V Thevenin's also. So as we know what is VOC, that is the open circuit voltage across the load terminal. So let us open here. Okay, and the same way, okay, you just apply the. So now we need to find the V Thevenin's or VOC. So it is nothing but the open circuit voltage across the load terminals. Okay, so here these are the load terminals. So we should open these two terminals and find the voltage across these two terminals. So across these two terminals means the voltage across the 5 ohms resistor. So if you know the current flowing through the 5 ohms resistor, then we can find V is equal to I into R. Then we can find the voltage across the 5 ohms resistor. So further here we are applying the loop analysis. So let us consider this is loop 1 and this is loop 2. Okay, then write the loop equations for loop 1 and loop 2. Okay, then find the values of I1 and I2 by solving these two equations. Then if you solve I2 is equal to 0.3, then V Thevenin's is equal to here 5 into 0.3, which is equal to 1.5 volts. Now we got the value of V Thevenin's and as well as the R Thevenin's. Okay, then we know just substitute these V Thevenin's and R Thevenin's values in the Thevenin's equivalent circuit and find okay the maximum power flowing through this circuit, which is P is equal to V square Vs square by 4R. So we know what is Vs square, which is 1.5, and R, of course, in both Rs is equal to RL, which is equal to R. So 2.5, then we can the maximum power flowing through that particular resistor is 0.225 watts. Okay, so here only the one difference, between the Thevenin's and maximum power is here the maximum power is represents the condition where we can get the maximum power flowing through the load resistance. When Rs is equal to RL, the maximum power flowing through the resistance, that particular load resistance. So as you can see here also we followed the same procedure as the Thevenin's theorem. So that's why if we know, or if you are clear about how to find the Thevenin's resistance and Thevenin's voltage, then it is very easy to understand or apply the maximum power transfer theorem and as well as the Norton's theorem. Okay, so I hope everybody get understood about these three theorems. Okay, in the next class we will discuss the remaining theorems. Okay, so don't forget these all theorems, okay, that which we are discussed till now are with respect to the DC source. Okay, of course the same theorems we can discuss with by replacing with AC source also, that we will see in the next classes. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.